oxidation-reduction reactions, or redox reactions. Oxidation-reduction reactions are simply a reaction in which electrons are transferred from one element to the other. The element that receives the electrons is said to be reduced, and the element that loses the electrons is said to be oxidated. This is an example of a common oxidation-reduction reaction. An iron nail is placed into a copper sulfate solution, and after the redox reaction occurs, your products are an iron 2 sulfate solution and a solid copper coating. And this occurs because the iron is oxidized and the copper is reduced. So the iron transfers electrons from itself to the copper. So what exactly is oxidation and reduction? Well, oxidation can be defined as the loss of electrons. And since electrons are negative, the loss of electrons results in an increase, because if you subtract a negative, you get a plus, in oxidation number. Now, oxidation number is closely related to charge, but it's not exactly the same, and we'll get into that a little bit more shortly. Reduction is the gain of electrons resulting in a reduction or decrease in oxidation number. Now, since there's no electron store where you can gain electrons and there's no electron donation spot, oxidation and reduction must occur in pairs, because one element can't donate electrons without having another element to receive them, and vice versa. You can't receive electrons unless there's another element willing to donate them. So these always come in pairs, oxidation and reduction, or redox. Okay, and this down here is an example of that. You have element A and element B, both with oxidation numbers of 0. And then after the electron transfer, element A, which has been oxidized or undergone oxidation, has a positive charge, or oxidation number, while element B, which has undergone reduction, has a negative charge, or oxidation number. Okay, so before you can determine what has been oxidized and what has been reduced, you must assign the oxidation numbers, and these are the rules that apply. The first rule is that elements found in their elemental state always have an oxidation number of 0. This means that elements that are not in compounds, like if you just have solid aluminum, its oxidation number will be 0. The elemental state also applies to diatomic molecules. So, like chlorine gas will also have an oxidation number of 0. The next rule states that individual positive cations and negative anions always have an oxidation number equal to their charge. So if you have a sulfide ion, for instance, sulfide's charge is -2, and so its oxidation number is -2. Rule number 3 states that alkali metals found in compounds always have an oxidation number of +1. So if you have a compound like sodium chloride, your alkali metal is sodium, and so it will have an oxidation number of +1. Alkaline earth metals found in compounds always have an oxidation number of +2. So if you have something like magnesium chloride, magnesium will always have an oxidation number of +2. And of course, these are also their charges, which makes it easy for you to remember these. Hydrogen, being kind of the outcast of the periodic table because it fits into so many categories and by then really no categories, can have an oxidation number of +1 or -1. When hydrogen is bonded to a metal, so like in the case of lithium hydride, well then hydrogen has to have an oxidation number of -1. When hydrogen is bonded to a nonmetal, like in water, then it will have an oxidation number of +1. Okay. Rule number 6 talks about oxygen. Oxygen, when in any compound with any other element, will always have an oxidation number of -2, just like its charge is always -2. So in water, we know that hydrogen is +1, and we know that oxygen is -2. Alright, and all of these rules 3 through 6, where it tells you what alkali metals, alkaline earth metals, hydrogen, and oxygen, what their oxidation numbers are in compounds, will help you to determine the oxidation numbers of anything else that might be in a compound with them by using rules 7 and 8. For a neutral compound, whether it be ionic or covalent, the sum of the oxidation numbers will always equal 0. So what that means is that the oxidation numbers, positive and negative, must cancel out. So if you have a compound like diphosphorus pentoxide, well, you know, because of rule number 6, that oxygen will have an oxidation number of -2. However, phosphorus does not fall in any of these rules, so you have to use rule number 7 to calculate the the oxidation number of phosphorus. So the way that you do that is you set all of this as if it were an equation equal to 0. So 0 equals, we know that there's 2 phosphorus atoms with an unknown oxidation number, plus 5 oxygen atoms with an oxidation number of -2. And when you add those together, they must equal 0. So you get 0 equals 2x minus 10, because 5 times -2 is -10, and so plus a -10 is the same thing as saying minus 10. So we need to get the x by itself to solve for it, so you must add 10 to both sides, giving you 10 equals 2x, divide by the number next to the letter, and you get that x equals 5. So that means that the oxidation number of phosphorus is +5. And a way to check your work is just to look to see that they cancel out. +5 times 2 is +10, -2 times 5 is -10. So yes, +10 and -10 cancel out to give you a sum of 0. So this works for any neutral compound, ionic or covalent compound. Rule number 8 applies to polyatomic ions. Polyatomic ions are covalent compounds that have a net charge. So instead of setting the sum of the oxidation numbers equal to 0, like for a neutral compound, you will set the sum of the oxidation numbers equal to the charge of the ion. So say you have an ion like phosphite. Phosphite is PO3 and has a charge of 3 minus. Now, the same rules still apply to oxygen. Oxygen is always -2. So we know that oxygen is -2. So now we're going to do the same thing we did up here, only instead of setting it equal to 0, as we would for a neutral compound, we're going to set everything equal to -3, the charge of our ion. So -3 equals, this time there's only 1 phosphorus, so that's going to be 1x plus 3 oxygens, each with a oxidation number of -2. So you get -3 equals x minus 6. And then to get x by itself, you must add 6 to both sides. We get x equals -3 plus 6 is +3. So in this case, phosphorus has an oxidation number of +3. So in diphosphorus pentoxide, phosphorus has an oxidation number of +5. In phosphite, phosphorus has an oxidation number of +3. So the only rules that are always are 3, 4, or the only elements that are always a certain oxidation number are alkali metals, alkaline earth metals, hydrogen, and oxygen. All the rest must be calculated using rules 7 and 8. And we'll practice these in class when I see y'all on Monday. Okay, now, if you're a little bit confused about what oxidation is and what reduction is, there's a couple of sayings that help you to remember these. The first saying is Leo goes grr. And this stands for, Leo stands for loss of electrons is oxidation, and then goes, and then grr stands for gain of electrons is reduction. Another way to remember it is oil rig. Oxidation is loss, reduction is gain. And of course this is of electrons. Now one more term that you will see in this unit is oxidizing agent and reducing agent. Because like I said, it always comes in pairs. So whatever is losing the electrons is said to be oxidized. Oxidation is occurring. But during that time, so say iron is being oxidized. Well, in that case, if iron is being oxidized, something else is being reduced, and so you would say that iron is the reducing agent for your other element. So whatever is being oxidized is the reducing agent, and whatever is being reduced is called the oxidizing agent, because whatever is happening to it, it is performing the opposite on the other element. So let's write that down. The element that is being oxidized is the reducing agent, and vice versa, the element being reduced is the oxidizing agent. Now that you know that this tarnishing is just the metal getting oxidized, all you have to do is reduce it. And all you need to do that is just some metal. Like aluminum? Perfect! Okay, now that we have some aluminum foil and some water, we can reduce our previously oxidized silver, or tarnished silver. Watch the science happen. And now we open it back up to check on our tarnished silver. Ta-da!
My bracelet's so shiny!
The once oxidized silver has now been reduced. As you can see, there are bits of aluminum oxide in the bottom of the foil from the oxidation reduction reaction.